Now we come to the next multi-user model. It's a multi-access channel. So we have 3 sources now and 2 encoder. Encoder 1 only receives W1 and W0. Encoder 2 only receives W2 and W0. Both encode their message into x1 to the n and encoder 2 into x2 to the n, and it goes over the channel, which have 2 inputs and 1 output, and the channel output y to the n, and the decoder must give some estimate of W1, W0, and W2. So let's look at the details again. The source put out the messages W0, W1, and W2. We have 3 sources with NR0, NR1, and NR2 bits respectively. So we have 2 to the NR0 messages from source 0, 2 NR1 messages from source 1, and 2 NR2 messages from source 2. And the message W0 is seen for both encoder, and we call it again the COM message. And the messages W1 and W2 appear only the respective encoder 1 and 2. So encoder 1 maps W0 and W1 to a sequence x1 to the n, and encoder 2 maps W0, W2 to a sequence x2 to the n. And the channel puts out the sequence y to the n. Now the receiver uses this output y to the n to compute estimates of W0, W1, and W2. And the problem is to find array tuples R0, R1, R2 for which one can make the error probability arbitrarily small. So we have one problem now, what we didn't have at the broadcast channel. We need synchronization because we require that yi is a noisy function of x1 and x1i and x2i. So the symbols must be sent synchronized from encoder 1 and encoder 2. So we can assume that there's a central clock, and this clock ticks n times, and x1i and x2i is sent at click, or it's clock tick I. And the receiving node sees it channel I output yi at clock tick I, or perhaps shortly thereafter. And you can think that the COM messages W0 might be strange because it's something which is just added to them. But we can view it also as a clock with rate 0. Or simple, we can also view it as another message that's available to both nodes. So where comes this model practical in? So one thing what one can do, one can view the MAC as being the reverse link of a cellular radio system. We saw that we can view this as a broadcast channel for the forward length. So it is somehow uplink and downlink. So uplink for the MAC and downlink for the broadcast channel. If there are 2 mobile stations, and the model describes the essence of the coding problem. One can easily extend the model for 3 or more stations, but we will only look at the 2 encoder case. And here is again some sentence about the common message. It might be presented as some common time reference to synchronize the transmissions. Then we have just the rate 0. Alternatively, this might represent information the mobile station are relaying from one other base station to the next. And the MAC was first considered by Shen in 1960. He introduced this model. The capacity region of the MAC for R0 equals 0 was found by Alswede in 1971 and also by Liao in 1972. And the capacity region, if R0 is greater 0, was found by Slepia and Wolf in 1973, and they have to use superposition coding. And we consider now the general problem, where the main trick is to introduce an auxiliary random variable u that represents the codebook for W0. And we consider distribution P of the joint distribution, the probability of the joint distribution u, x1, x2, and y that factors as pu, px1 under condition u, and px2 under condition u, and py under condition x1 and x2. So what is now about the code construction in the general case? So we consider this probability of the auxiliary random variable u, and this u denotes the alphabet of the random variable u. And we generate 2 to the n R0 code words again, u and w0, by choosing ui w0 independently using pu for each I from 1 to n. And for each un w0, we generate 2 to the n R1 code word, x1 to the n of w0 and w1 by choosing the x1i w0 w1 independently using this probability distribution x1 under the condition u. Similar, we do the same for 2 to the n R2 code words. So, and the encoder again, so you look and you see that this is the same thing we did before somehow. So the encoder now given W0 and W1, he transmits now x1 to the n of W0, W1, and given W0 and W2, encoder 2 transmit x2 to the n of W0 and W2. And the decoder, he receives some yn, and his goal is to receive a triple W0 tilde, W1 tilde, and W2 tilde, such that this un, x1 to the n, x2 to the n, and y to the n is jointly typical, considering the joint distribution of u, x1, x2, and y. And if no such triple is found, if one triple is found, then choose one and call it W1, the estimate of W0, the estimate of W1, and the estimate of W2. If no triple is found, then we put all 1, but this will happen very seldom. So you see that nothing is somehow new for us. So for the analysis, we know that with probability close to 1, we will have that u to the n, x1 to the n, x2 to the n, and y to the n is jointly typical concerning the joint distribution of u, x1, x2, and y. For the transmitted triple W0, W1, W2. As long as the probability factors as we have specified before. And now the remaining analysis is very similar to the degraded broadcast channel. And we do it every time that we split the error probabilities. Here we split it into 7 disjoint events that correspond to the 7 different ways in which one or more of the wi from I equal 0, 1, and 2 is not equal to wi. And these are all errors. And for example, we can look at the event that w tilde is not equal w0, but this is jointly typical. And note that all 3 code words were chosen independently actual to the transmitted code word. And we can upper bound this probability then by this formula here. And I think you all can do it now. You just look at the thing what we did for the degraded broadcast channel and what we did before. All this estimation, there's nothing new to be done. So therefore, I come now with the 7 inequations what we have. So we have R0 is less or equal than the mutual information of x1, x2, and y. R0 plus R1 is bounded in this way. R0 plus R2 is bounded this way. This is somehow the first part of the channel. It's from encoder 1 to the decoder. And if you look at encoder 2 to the decoder, we get these inequalities here. And in totally, we get these inequalities here. And again, one can restrict to some auxiliary alphabet, which is less or equal than the minimum of the cardinality of the output alphabet plus 3, and the cardinality of x1 times x2 plus 2. And if you look at the result, it looks like this. We have somehow 7 phases, 4 of which arises from the first inequalities, and 3 of which are non-negative constraints on the rates. So in general, we can achieve all these rates, and what we can choose is this probability. And we take the union of all this rate, and we get this rate region here. Now we have to show the converse.